Welcome to Espresso and Electronics, quick sips of EDA wisdom. So today's episode is very special to me because we talk about the evolution of verification techniques, right from logic gates to AI gates, the journey of verification in EDA. I'm your host Anika Sunda, and joining me today is Matt Graham, Product Marketing Director at Cadence in SVG Group. Welcome to the show, Matt.
Thanks very much for having me, Annika.
Absolutely. It's a journey that has taken us, Matt, from manual checks of early days to sophisticated AI and ML processes of today, right? And you have been a veteran in this space, right? So let's start from the beginning. Let's hear it from you that verification was a manual process, a tedious process, right? I mean, what is it that you feel has changed over these years, right?
Absolutely. So, I mean, I have to admit that, I've been in the verification space for probably 2.5 decades, and certainly, verification and logic design, predated my entry into the industry. And I joined at a really interesting time as we were just moving from incredibly manual and very tedious processes of waveform inspection and manually looking at log file and output from the simulation level, and moving into an initial era of automation where we're using things like object-oriented programming languages and constrained random verification and things like coverage. So this was the first level, when I started, 25 years ago, of automation going from, like I said, very, very manual to some level of automation and abstraction. And that was my introduction. I was a Specman guy way back when, and I was part of a team that brought into the company I worked for at the time this idea of a very automated test bench. And certainly we weren't, the very, very first, but we were on a leading edge at the time, to what has become very commonplace today, where almost all verification engineers are using something like SystemVerilog and UVM. They're using software programming techniques like object-oriented to enable automation and randomization. So we're no longer manually writing test vectors, and we haven't been for a couple of decades, at least for the majority of verification. We're no longer manually inspecting waveforms for the vast majority. We are, generating legal constrained random stimulus. We're automatically checking the output, and this is all in terms of simulation and emulation, of course. And so we've seen that leap of automation, and we used to talk about back in the days when I worked at Versity, the verification maturity scale, right? There was this idea of just running vectors and manually inspecting results all the way up through sort of a coverage driven approach where you could randomly generate stimulus and capture coverage. And on that scale, we didn't consider things necessarily like hardware software co-verification. We didn't consider formal techniques and all these other things that have come in the meantime. And we certainly never, 20 years ago, foresaw the opportunity or the impact that things like AI and ML might have.
Absolutely. I think in the early days, if I remember clearly, it was all about your peer reviews, right? I mean, we heavily
Mm-hmm.
relied on our peers, right? I mean, like, okay, I mean, I've written a code, let me just get it reviewed by my peer. And I think all the designers were using manual checks, right? And they were absolutely relying on their two pair of eyes, right? Or their expertise to catch errors. I mean, it was quite error prone, I believe, and it was quite time consuming. I mean, frustration, I think, was too high, right? Because you verification is not 100% complete, right? So you try to do as much as you can, but then you're only relying on your pair of eyes and some other peer reviews, right?
Absolutely. I mean, humans are very error prone by nature. I mean, I certainly am. You can ask my wife. I make mistakes on a regular basis. Probably minute by minute if you ask her. But you're absolutely correct. I mean, again, as you stepped up what that sort of automation and abstraction, it was we would remove the human error at one level, but then we would introduce it at another. So when we went from just writing vectors, so like you say, you would write a bunch of test vectors and you would get a peer to review it. You'd have a code review meeting and everybody would look through it and say, yeah, did you write the right vectors given whatever it is that you wanted to test? And then we went and we said, okay, well, now let's move to constrained random stimulus generation, to where we've got a bunch of random variables. We have a bunch of constraints that define the legal parameters or particular test that we want to write, a particular area of the design we want to explore, and then you would have your peers review those constraints, right? You had to go through code review for the constraints and the test, and then it was a code review for the coverage, and on up the chain as things like Verisium Manager from Cadence became available. You would write a verification plan, and then you'd peer review the verification plan that would outline, what coverage you needed to write, which would drive what stimulus you needed to write. And we kept, this whole idea was to provide this kind of as you provided abstractions, you got further and further away from a human error at the individual bit level. And the idea with the, as you went up the chain of abstraction, if you could, for example, peer review and say, we wrote good coverage, well, that was going to drive that you would then have to write good constraints to hit the coverage, and you would have had to have write good verification environment to be able to achieve those constraints. And so therefore you didn't have to look at vector by vector, was the vector correct? You could look at higher levels of abstraction. And that really helped move away from the reduce the amount of tedium. But in reality, that enabled us just to do bigger and bigger chips, right? We were, a billion gate, whatever it is, SoC, you weren't going to be able, to write and review vectors for that entire thing. You were going to have to rely on abstraction of some level, and that just allowed us to get bigger and bigger. And so now the amount of time that 30 years ago we would have, or 25 years ago, we would have spent reviewing vectors, we're now spending that at least that much time reviewing coverage, reviewing verification plans, whatever it might be, at the higher levels of abstraction.
Yeah. In fact, I just remember a PJ, right? I mean, when we were verification engineers, I mean, long time back, I remember, I mean, there was a joke, right? I mean, what's a verification engineer's favorite hobby? And so it was like fishing, but instead of fish, they are just catching bugs, right? And just like fishing, the big ones always seem to get away. So,
Yeah,
like,
absolutely.
uh, moving ahead, right? I mean, what was the biggest or the strongest pull that like you feel that made all of us push, to make the verification process a bit less daunting, right? I mean, you know, was it the chips getting bigger, complexity, or what was it, right? I mean, I mean, industry was running before also, right? I mean, people were working, the jobs were getting done, everything was there, right? But what was the major push, if I would ask you?
Yeah, well, I don't think there was a big. I don't know that there was a massive watershed moment where we jumped from one to another. But I think it is just the fact that, so yeah, obviously Moore's law continues to drive, or continued for a long time, and you can debate whether Moore's law is running out of steam or not. But it basically said, look, devices are getting larger and larger and larger, and they're going to continue to do so, right? The number of transistors in an individual chip is going to continue to double every however often, and even if the physics starts to run out of steam, then we're going to come up with other capabilities like 3D IC or chiplet multi-die or whatever. There's always going to be something. And with verification, if you double the gate count, you square the state space, more or less, right? Which means that grows exponentially. So you couldn't just add, if you doubled the gate count in a device, you couldn't add 2x the number of verification engineers and continue on in with whatever methodology you had. There was just too much, just too much content, too much work to be done. And you couldn't double your team size anyway, even if you wanted to. The talent just doesn't exist, and our ability to hire good verification engineers is not that fast. And so we had to develop as an industry, develop new and more interesting techniques. And then as these, the verification task became exponentially larger, we had to expand into looking to other than just simulation. We had to look to first emulation, prototyping, of course, formal methods. Can we mathematically prove that a particular part of the circuit or a part of the chip or maybe the entire chip is bug free? And we had to expand our view to verification engineers not just being engineers that ran simulations and checked dynamic test results, but they did all these gambit of things. We had to get better and better lint rules so that the code that we were starting to verify was going to be better and less buggy. We had to get like I said, a number of different formal applications, not just proving circuits, but things like connectivity and sequential equivalency checking and register verification, static register verification. all of these things enabled us to grow the size of the device that we could verify in a given amount of time. I think the other thing is that what's changed from definitely in the electronics industry from say 30 years ago is that 30 years ago, first of all, mobile phones were very nascent, but also devices coming to market were on a much slower
Yeah,
pace.
exactly. Yeah.
As your home PC, you changed every 5 years, maybe, right? Your video gaming system, a new one came out every 3 to 5 years. There was definitely there was very little in terms of connected home. Industrial applications were decades long. We've switched now to a case where if somebody has a mobile phone or mobile device, a smartphone, whatever you want to call it, that's more than 2 years old, you go, wow, you've got an
Exactly.
antique there.
Yeah.
So so we see companies that are doing mobile phones, that are doing televisions, that are doing consumer of any kind, automotive, whatever it is, the turnover cycle is much, much faster. So the devices got bigger. Our ability, our need to get them out on time as an industry compressed significantly, and so we were just forced to develop all of these techniques. I mean, it's absolutely required, for example, that the new whatever it is mobile device be ready for
Yeah.
Christmas every year or for whatever the shopping season is, wherever you might be, and as a result, that electronics needed to be ready at that time, and so we just didn't have a choice. And I am a firm believer that necessity is the true mother of all invention, and when you
Invention.
when you give
Yeah.
somebody a problem, smart people will go and figure out a way to solve it, and that's how our industry has expanded and continues to expand.
Yeah, yeah. No, absolutely. I mean, in a household, I think it's a competition, right? Oh, you're using iPhone 13, oh, I'm using 12, oh, I should upgrade, right? I mean, I was like, you don't need to, right? Like,
Yeah,
no, it's
absolutely.
just this. Yeah, I mean,
Yep,
okay. Yeah,
absolutely, absolutely.
yeah. But also, having said that, Matt, I mean, formal verification, I remember brought, some degree of assurance, right? I mean, that was
Mhm.
previously unimaginable. I mean, especially for complex systems, right? Where the room for error was virtually nil. I mean, like what do you have to say about formal, right? I mean, some people think that, okay, I mean, formal can do everything, right? I mean, but I don't think that's the case, right? I mean, there is only a specific need that formal can do, but then for certain thing else you need simulation or maybe hardware or prototyping, right? So I mean, like for example, a painting, right? It needs different paint brushes to do different strokes, right? I mean, similarly, I think it's with these engines, right? So what about formal? I mean, what do you have to say for formal?
So I'll agree 100% with your analogy about paintbrushes. I'm a bit of a car guy, and certainly I don't work on a car with just a screwdriver or just one kind of screwdriver.
Yeah.
It's you need an entire toolbox, and verification is no different. I think formal has a very, very significant role to play, and we see that role expanding, all the time. Now, will we ever get to the point where you can verify an entire SoC without running any dynamic simulation? Because of course, I mean, the nirvana goal would be we can mathematically prove that an entire SoC is bug free. Because of course, formal, it's not with simulation. You're saying I ran all these simulations and no one has failed yet. None of the simulations have failed yet. Whereas, with formal, when you prove something, you say, I have proved that this can never fail. And so clearly that, from an engineering standpoint where I want all of my angles in my life to be at 90 degrees, absolutely formal is the dream, right? We can just put a circuit into the formal engine. It says, yep, based on your constraints, this can never fail. But that is at least today, that's not a possibility for the size of our devices, and the devices keep growing. Now, the size of the circuit that formal can prove continues to grow as well, which means that more and more significant portions of the logic can be formally proven. And you're right, there are certain critical parts of the of a circuit of a given chip that for which formal is probably at this point mandatory. You think of things like uh, memory management, arbiters, certain pipelines in a processor, et cetera. All those things are going to require this formal property verification, or what we would think of as classic formal, right? We literally prove that this circuit cannot fail in whatever conditions that we've described. I think formal will continue to grow in terms of its applicability in different areas of the verification process as well. I mentioned things like connectivity checking and equivalency checking, sequential equivalency checking and things like that.
Mhm.
I think it's all those things are definitely, formal is going to be a key tool. And it's not going to be where, 15 years ago, maybe, that it was A, the domain of experts, and B, it was the third tool you reached for. I think it's now becoming the first or second tool you reach for as a verification engineer. Certainly, it's available for providing results before a test bench is ready. It's available earlier and earlier in the process. It's applicable later and later in the process as well. And I think,
Yeah.
my prediction would be that will it displace simulation as the number one tool that verification engineers use? I don't know that it'll ever approach that, but I think it's more and more it is becoming
Maybe it's like a
a
hand in glove, right? Might
yep, exactly. It
be
is more and more becoming, like you say, hand in glove is a great analogy. It is becoming that more and more. And I think any verification team that ignores formal does so or doesn't use it does so at their peril.
Yeah, yeah, absolutely. So it's really fascinating to see how far we've come, right? And
Mm.
as we look to the future, I mean, what do you predict for the next evolution in verification? We are hearing so many things, right? I mean, Chat GPT, LLMs. I mean, AI is everywhere. I mean, people even feel threatened, right? Like, will AI take over my job and all that stuff, which I think is not going to happen. But still, I mean, what do you predict for the next evolution, the next wave?
It's an excellent question, and first of all, I think there is the fundamental engines, the simulation, the emulation, the formal engines, and so on, will continue to evolve and grow, and I think they will continue to be the workhorses of verification. So my first prediction is that chunk of EDA is not going anywhere. Nobody's going to replace simulation with something in the next 5 years. That would be prediction number one. Prediction number two, I would say, is that, I think we're going to see that AI is a very valuable tool, but it is not nearly as valuable as the amount of excitement and hype around it right now for verification. Now, for other parts of our world, and other parts of technology, I think it absolutely has it can potentially approach the hype. But for verification, I think that it's not 18 months away. It's maybe 5 years, 10 years before AI, generative AI at least, this idea of Chat GPT and things like that, truly replacing uh, engineers on any kind of level, or substituting for engineers. I don't think any of us is going to be replaced with such a dearth in the market. There's so much demand right now that I don't, even if AI did what the hype is, I think we'd still need all the engineers to
Yeah,
either build the AI or
because there's
whatever.
no authentication, right? You type something and you get a response.
No,
I mean, who is validating
no,
that this is the right thing, right? I mean, so yeah.
yeah, not yet. And that's maybe, if I think that is where AI and EDA is going to sort of come together, in that I think EDA is going to have to develop these capabilities to say what comes out of AI is valid, is valuable,
Exactly. Hmm.
is correct, or whatever it might be, to provide that validation, right? I also think that there's an opportunity to catalyze, and we've been saying this at Cadence for a little while, to catalyze the engineer in the loop, in the interim, right? I think that AI has the ability to significantly improve the productivity of engineers in the relatively short term, right? Then that, certainly we see the beginnings of that now. We're going to see that in really solidify over the next, let's say, 2 to 3 years, where we're going to see order of magnitude improvement in formal and sim efficiency, in debug efficiency, in CPU and farm utilization efficiency, based on AI. But that's not going to be necessarily generative AI. We're not going to say, oh, we've eliminated this engineer because we can just generate
Yeah.
RTL. Be some of that, but I think the big contribution over the next 3 to 5 years is, or actually the next 6 months to 5 years, is in that productivity. Where what used to take 10 hours to debug in waveforms is going to take an hour, because AI will have helped that engineer get that much closer to the root cause. What would have taken 24 hours of simulation is going to take 3 hours because AI will have optimized what tests you need to run, how they are run, what resources they need to use, and so on. And I think that's where the big impact is going to be in the next, in the short term. The longer term, it's going to be the generative AI things where we can, start to literally, what would have taken an engineer sitting typing at a keyboard can be replaced by AI. But I think that's, where that will become a majority or even a significant minority, I think is further out than some people are giving it credit for, that the hype would have you believe. But
Yeah.
you know what? I've been wrong lots of times before, so we'll see how that plays
No,
out.
I mean, yeah, I mean, I remember, I think you also remember, right? Paul Cunningham, right? I mean, he mentioned that let machines do things that they're good at, right? I mean,
Yep,
let them do what they're good at and let humans focus on what they are good at. I mean, I mean, AI, ML, LLMs, all I think can be useful tools to maximize productivity and our efficiency, right? I mean, and utilizing the manpower to something more better or something,
absolutely,
yeah, more productive.
absolutely,
Okay,
totally
so,
agree.
yep. Thank you, Matt, for the insights. And yeah, thanks to all the people who are listening to our podcast. So keep your circuits connected and your ideas flowing until we meet again on Espresso and Electronics. Stay
Thanks very
innovative.
much, Annika.
Thank you, Matt.